right, this is lecture 2 of the 7.7 equilibrium material. So we're going to move on and talk about doing these ice box problems with concentration. So this problem is very similar to the partial pressure, except for we're going to use concentrations. One of the first things we note is we have that really small Kc value, which means tends to hang out over on this side. This is a molecule that has some historic significance. It's a carbon with double bonded to an oxygen with 2 chlorines, so it's a nice symmetrical molecule. However, as you can see, it has the potential to be deadly. Chlorine gas is a deadly gas. And this was used in World War I. They say about 85% of the deaths, there's about 91,000 people died from poisonous gas estimated. And it was just horrific to the point where they made rules that you can't do that in war anymore. So that was World War I, initiated by the Germans, and then other countries kind of followed suit. But phosgene was the most commonly used, and one of the more deadly ones was mustard gas. Hopefully you know enough about equilibrium where you're questioning the effectiveness of using this if so small amount of chlorine gas is produced. And that, in fact, is true. This reaction would not be deadly. You could have some phosgene sitting in the classroom, and we'd be okay. A little bit of extra carbon monoxide, a hint of green chlorine gas, but such a small amount with this kind of equilibrium constant. So this guy, it wants to stay like this. So put that on hold. We'll talk about how phosgene was a very effective deterrent in World War I, but it's not this reaction. It's coming up. Okay. So anyway, we look at this. We don't have a concentration. We have the moles, and we have the liters. So it's supposed to be a molarity problem. So the first thing you're going to have to do is find the moles per liter. Well, that's a simple calculation. You do have to watch those sig figs again. So you get that the concentration, if there's that many moles per 5.8 liters, you divide them out, round it, so that you have 3.3 times 10 to the minus second molar, capital M, moles per liter. All right, so now you are ready to do your ice box. And see if you can use what we did in the first problem with the partial pressures. See if you can't fill in this ice box with the x values and the final change in the equilibrium constant. See if you can give it a shot. All right, hit the pause. So hopefully you wrote this in here. Notice they didn't write M in. You do not have to put the concentration with the gas. We put ATM in there just as a clarification. But you don't have to. This is a numerical tool that you're using to do some calculations. So you can just stick with the numbers. That's my initial concentration. And over time, you're going to get some of this, but it is very, very small. Okay, so let's, hopefully you got this. The coefficients in this chemical equation are 1 to 1 to 1. And again, I prefer putting the actual chemical equation in there, which in this case is pretty much the same thing. If you look, if you just write in that equilibrium equation, and then you got your 1, 1, 1. I don't think it's helpful to have the square brackets in this part. So just write your equation in there, and that actually can be as useful as anything, because now you'll know the states that they're in for when you write your equilibrium expression. So anyway, hopefully you did this, and you said 3.3 times 10 to the minus 2 minus x, because that's what you started at, and you're going to subtract x from it. You're going to add x, and you're going to add x. So both of these guys are x. The temperature is 0. So we got above 0. Now it's going back down to 0. Dang it. It was nice while it lasted. And I got to go pick Mariana up from basketball. She's at Mankato tonight. Feel bad for the varsity. That's going to be a late night. So anyway, you've got this phosgene. How much will it decompose naturally at room temperature? Well, you use the Kc, and you put the products on the top, the reactants on the bottom. There are no coefficients to mess with here. You do, however, have to make the assumption that this x is going to be really, really small. We're going to guess that it's going to be less than 1 times 10 to the minus 4th. Again, that's sort of a cutoff point for it to have no meaning, because again, you're subtracting, so it's about place value. So if your place value is, I mean, this is pretty small number, so you got to be kind of careful, but we're guessing x is going to be even way, way smaller than that, to the tune of less than 1 times 10 to the minus 4. And again, it doesn't hurt to guess, because when you finish it, that's not right, then you just have to go back and redo it using the quadratic formula. Dun, 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 dun. A lot of songs helping you in this. Ice, Ice, Baby, and that, whatever that weird quadratic formula song is. Okay, so what we have here is a little bit easier math than we had in the last one. It's just x times x. So go ahead and plug in and solve, and then these concentrations are actually going to be the same. So that part's a little simpler as well. So hopefully when you crunch the numbers, you got 4.9 times 10 to the minus 20th molar, which, of course, equals your concentration of your carbon monoxide and your chlorine gas. This is probably within EPA levels of being safe levels of chlorine gas and carbon monoxide, very, very small amounts. And these would be extremely difficult to measure. So that's where these sort of algebraic type of problems where you just plug in the numbers are useful, because actually being able to measure those amounts would be a difficult thing to do, certainly with the things that we have here. Now, and thirdly, remember the phosgene is not going to really change its concentration. Yes, it does change a little bit, but certainly not within the degree of accuracy we have with significant figures. So, was this a correct assumption? Is 4.9 times 10 to the minus 20th less than 3.3 times 10 to the minus 2nd? Yeah, it's way less than. Okay, so it would have no effect on the concentration of COCl2, and it was an okay thing to assume that as being 0. And then you can just check it to see how close we come up with. Not sure where they got the extra sig fig here. 2, 2, and then this has 3. I would call that 7.3 times 10 to the minus 38. And then if you go back, they had 7.27. So to our degree of accuracy, yeah, that worked real nicely. Okay, so again, using that ice box to make these calculations. It's going to be a super important skill moving forward, really all the way up until the end of April, which is the end of AP. We mentioned that we were going to do a conclusion on the phosgene gas. So this slide here shows the reaction we just talked about, and here is the horrific thing about phosgene. If it comes into contact as a gas, so this is why we can't have it in the classroom, because it wouldn't make a lot of Cl2 and it wouldn't make CO, but if anyone has any moisture on their body, it reacts extremely well with water to make carbon dioxide. Nobody hurt there. Whoops. Aqueous hydrochloric acid. So you might have history buffs know that many of the soldiers in World War I suffered blindness because guess where there's a lot of moisture in and around your eyes, and basically having that phosgene gas was like putting acid in their eyes. And the other place there's moisture, when you breathe in all that moist tissue in your mouth and lungs, it was kind of like drinking acid and breathing in acid. That was the part, and I don't want to dwell on this because it really was a horrific way for these soldiers to die. And we're talking on the order of about 70,000 or more soldiers died from this inhalation of basically what turns out to be acid. But that's the difference. This is not equilibrium system, and this one is. So sort of a intriguing historical perspective on this. All right. So moving forward, I will post the answers for 7-7 problems for you, and that assignment you get the 2 days, so that's going to be due Friday by 9:10 a.m. All right. So don't fall too far behind. All right. We will see you guys. Just moving ahead, I think we're probably going to do Friday, Monday lab on equilibrium chemistry. So that'll be kind of fun to get another lab in so that we can continue to sort of catch up on some lost time in the laboratory. All right. So have a good one. Enjoy your above zero Wednesday.